Okay, so while people are still trickling in, we'll get started. So our speaker today is Nick Pedatella from the High Altitude Observatory. Nick received his PhD from CU in 2011, and he was an ASP postdoc for a few years in HAO, and then joined the UCAR Cosmic Program Office, and then returned to HAO back in 2016 as a scientist. It's funny, I've actually known Nick for a long time through running, actually, when he was a ASP postdoc, and for some reason we have converged again at NCAR. So I'm really excited to have him present to us today this data assimilation in WACCM and WACCM-X implementation and science investigations. And before I hand it off to Nick, just to say, if you have a question or clarification, you can feel free to say something in the chat, and we can catch that. And then for the questions at the end, if it's okay with everyone, I would like it to be organized. So just write in the chat when we do the Q&A that you have a question, and then we can all just all speak individually instead of all trying to speak at once. So Nick, take it away.
Okay, thanks for the introduction and for asking me to sort of fill in, I guess, and give a seminar while we're all at home. Just one sort of comment or clarification. I can't actually see the chat window when I'm in the presenter mode. So if you do have clarification during the talk, if it's a minor point, I guess you will just need to speak up. So typing into the chat, I would not see. Yeah, I will present some work from the last few years on data assimilation in both WACCM and WACCM-X. And before starting, just like to thank the several people who have contributed, especially Jeff Anderson and Kevin Rader and the DART group in CISL. They have helped quite a lot in terms of implementing this. Also Honey and Dan, and then some collaborators in Taiwan, and then another group of collaborators on some of the work for the transport of NO. So as first kind of just brief outline, I'll give some background and motivation, then give an overview of WACCM and WACCM-X and DART, which is how we implement the data assimilation. And then I'll focus on kind of two scientific areas, application. First being the transport of NO during sudden stratospheric warmings, and then also look at MLT forecasting. There's some other work more related to the ionosphere, and I try to focus mostly for sort of ACOM, so won't discuss too much about that part. So as a kind of general motivation, we always want to, oftentimes we want to be able to reproduce the variability of the atmosphere in whole atmosphere models for specific event studies. Rather than running the model free running, we want to reproduce specific event for look at different couplings or things like that. And this is really because the observations that we have are limited, so we can't study the real world completely from an observational perspective itself. But of course, simulations have a lot of uncertainty, so we want to be able to essentially constrain the simulation so that it reproduces something as kind of close as possible to truth, and then we can use that for various types of science. So there's two kind of approaches that this could be done. The first being nudging towards an existing reanalysis. This would be similar to this sort of specified dynamics type approach, and these are quite simple to implement. and they're relatively inexpensive in terms of the computational cost. The nudging does not add that much cost. The one downside is you're sort of relying on an external model and the kind of fidelity or features of that model. So if the model only extends to a certain altitude, you're sort of restricted to only constraining within that domain. The sort of alternative approach would be data assimilation. This would be what is used in numerical weather prediction type of models. There's various variational approach, 3D var, 4D var, and then different ensemble methods. Of course, these often can maybe give a better representation compared to just nudging, but of course they're a bit more complex. It adds some computational expense, but they are more flexible, and you can potentially constrain the model where existing reanalyses don't exist. So there's further motivation of why you would want to constrain the model. Most reanalyses, of course, only extend up to say 50 kilometers or so. So for example, when we do a specified dynamics type of simulation in a model like WACCM, you can only constrain to a certain height, and then above that you're relying on all information to be propagated from the lower altitudes to completely constrain higher altitudes. And this is not necessarily a fully valid assumption. So these are basically looking at error in a perfect model experiment. These are results from some work done by Ann Smith, showing that on the left is the temperature error, looking at if you the black here is a free running simulation compared to the truth. And then if you nudge just in the troposphere, or say up to 50 kilometers, you'd see that in the mesosphere, you still get essentially large errors. So this idea that you just can fully constrain the higher altitudes by constraining the troposphere and stratosphere is not a fully valid approach. So ideally, we would want to be able to constrain the higher altitudes, and you can see if you constrain the model still to higher altitude, you reduce the error more in the mesosphere. So if there's ways we can constrain this data, constrain these altitudes using data rather than nudging towards reanalysis, we can get better representation. And most of this turns out to be due to smaller scale waves, as shown here on the right, where if we just introduce basically constrain based on relative friction, you get a much lower error when you do the nudging compared to more sophisticated gravity waves. And this is not just true for sort of perfect models. This is comparison here, where these are 4 different whole atmosphere models. This is a zonal mean, zonal wind result average over about a month-and-a-half period. And you can, these I should say are not free running, they were all constrained to some sort of reanalysis. But you can see though they're quite consistent, say in the troposphere and stratosphere among the different models. As you get to higher altitude, there's quite large discrepancies among the different models. So this is basically, again, how they're transferring information from lower altitudes to higher altitude. It's a larger error in these and altitudes. And if we look at the zonal mean gravity wave drag, it's again quite different between all the different simulations. And this is likely what's driving these differences in the mesosphere among different models. And this is just another depiction where if you look at the altitudes where this is now a time series in the northern hemisphere. This period is the 2009 sudden stratospheric warming. And if we look at, kind of below in the grayish shaded area where the models are constrained, there's good general agreement among the different simulations. And here is the aura MLS temperature observation. There's general agreement there, but again, at higher altitudes, there's a lot of discrepancy among the different simulation. And this is, again, likely due to the differences in gravity wave drag. But these large differences essentially, inhibit perhaps how well you would trust the information coming from these models and how well they're really reproducing the state of the atmosphere. And these dynamical differences that I show in the last few slides, say in winds and temperatures, also have a lot of impact for things like chemistry in the mesosphere and lower thermosphere. This is example where the top plot, so these are from WACCM simulations, looking at the nitric oxide descent following sudden stratospheric warming in 2009. So in the top plot, the WACCM was only nudged up to, say, 50 kilometers, and you see this is kind of a weak NO descent. But in the bottom panel, they use a higher altitude reanalysis to constrain the model. So now the dynamics are presumably better specified throughout the mesosphere, and you get a much better representation of this downward transport of NO compared to if you're just nudging here. So in addition to just getting the dynamics better, you get a better representation of sort of mesosphere chemistry if you can constrain the model at higher altitudes. And again, I won't talk much here about the ionosphere, but better representation of the mesosphere can lead to a better depiction of the ionosphere variability. These plots here this is again during a stratosphere warming time period. This is the vertical plasma drift at about 300 kilometers altitude at the geomagnetic equator. This is local time versus day of year. And the top is a specified dynamics WACCM-X simulation. And then the middle is if we do data assimilation. So we would have a better representation of the mesosphere, as I'll talk about here soon. And then the bottom panel is observation. And you see we get much better representation of the ionospheric variability in this case where we're better constraining the model using data assimilation compared to just specified dynamics. So the idea is that if we can do direct assimilation of lower, middle, and upper atmosphere observations in WACCM and WACCM-X, this essentially gives a improved simulation of the MLT dynamics and also then chemistry, and then also in the ionosphere and thermosphere. So now I'll just briefly discuss the implementation of WACCM and WACCM-X using DART. So in general, the implementation is quite similar in WACCM and WACCM-X. So a lot of what I will discuss is kind of interchangeable between the two. So that, just for those who are not familiar, data assimilation is essentially a way to bring in the observations and combine them with the model to improve the representation of the state. So here on the top is just a graphical depiction where we have observations that during some time window we data assimilation, and then we get a set of what are often referred to as analysis fields, which would be basically merge the background model with the observation to give the best estimate of the current state. And so here you would maybe, for example, have some winds. You get to this point and then adjust them based on the observation. And then you run essentially a short-term model forecast to the next period when you do data assimilation. Again, combine it with the new set of observation to get new analysis fields and kind of continue this cycle. So in WACCM, we've implemented this using the DART ensemble Kalman filter. So at each of these steps, we basically have a set of analysis fields. So basically a full ensemble, and then we run a full ensemble of model forecast. This does, of course, mean it's a bit more expensive because you're running a full ensemble of models in the forecast step. So instead of running one instance of WACCM, you may have to run 40. But one advantage is that we don't need to specify the background covariance information because it can come directly from the ensembles. So this saves some of the sort of development in terms of the data assimilation itself. And the utility of doing this is we can basically create observationally constrained analysis fields. And then these can also be used to provide initial conditions for ensemble-based forecasting. So in terms of the observation that we assimilate into the model, in the lower atmosphere, say stratosphere and mesosphere, or troposphere and stratosphere, we include the conventional lower atmosphere observation. So these are things like the aircraft temperature and wind data, radiosonde data, and then also the cosmic refractivity. One thing that is not assimilated in these lower altitudes is the satellite radiance data. So that has some implication in terms of the sort of quality of the analysis fields at lower altitudes, because that's a big source of data for sort of modern numerical weather prediction. So we tend to do a little bit less well because of not assimilating that data. At higher altitudes, we have the temperature data from the Aura MLS satellites, and then also time saver. And so this is really a key data source going up to 100 kilometers, which really helps better, as I was saying, we want to be able to better constrain these altitudes above where there's kind of existing reanalysis data. So a lot of that comes from these two satellite instruments. And then recently there's, in WACCM-X, have implemented capability to assimilate ionosphere data from both cosmic electron density profile and then also ground-based total electron content. So in terms of how WACCM and WACCM-X DART perform, these are some plots looking at the troposphere performance. So on the left, this is a 10-day period that we ran the simulation, looking at basically the root mean square error relative to radiosonde observation. So the top panel is a forecast, so short-term forecast, so a six-hour forecast, and then the bottom are the analysis, and this is global average. And you can see the errors are on the order of, say, 1 Kelvin. Most people may not be too familiar with, sort of a modern numerical weather prediction, how they would perform. They would tend to be a little bit better, but not drastically better. So we're kind of in the range of what you would expect. And then on the right, panel, this shows the 500 hectopascal geopotential height as a snapshot in latitude and longitude. And the top panel is the NCAR reanalysis, and then bottom is WACCM DART. And you can see that in general, where say these high areas of high geopotential height are quite consistent in WACCM DART with what we see in the reanalysis. So this gives us some confidence that what we're reproducing in the troposphere in a data assimilation version of WACCM is consistent with what you would see in a reanalysis, at least in the troposphere. And we can, as I mentioned, the main interest is looking at higher altitudes. So we can look at how well the model performs basically in the mesosphere. So these are results for 5 times 10 to minus 3. And the top panel is a bias, and these are relative to SABRE observation for a 10-day period. And the different lines here indicate different experiments. So if we don't assimilate any middle atmosphere data and only constrain the lower atmosphere, this would be something similar to basically a specified dynamics type simulation. You get a bias relative to SABRE of here something in the range of 10 to 20 K at this altitude. But if we do assimilate SABRE, you significantly reduce the bias. So the solid line here is the 6-hour forecast, and then the dashed line is the analysis. The analysis. So if we assimilate SABRE data in the red line, you get a significant reduction, and with both SABRE and MLS, you can see we essentially reduce the bias to near 0. So this is showing that by assimilating the data, we can significantly reduce this temperature bias. The bottom panel shows a bias relative to aura. And so a key point here is in this red, where we're only assimilating the SABRE data. And in that sense, aura is essentially an independent comparison that you're validating against. You see we significantly can reduce the bias in this red line compared to the no assimilation. It does not quite go to 0, but it's significantly reduced. So this illustrates the sort of value of assimilating these data for better constraining the mesosphere. This is just another depiction where, again, here is essentially climatology. This is now just a single UT where we have latitude versus longitude. WACCM climatology on the upper left, and data assimilation upper right, and then the 2 sets of observation that would be assimilated from SABRE and then MLS. And you can see the observations are much more showing tend to be in this sort of blue, green, yellow type of colors, versus the climatology, which tends to be a bit higher. And then in the assimilation, we get something that's much more lower compared to climatology, consistent with the observation. So you can see that by assimilating these data, we get a much better. We can remove this temperature bias in the mesosphere. One thing to note is, this is the amount of data that would go into the mesosphere at a single snapshot. So you can see it's still quite sparse, which is going to have some implications in terms of how well you can really constrain the mesosphere, because you don't have data really everywhere. You still have a fairly sparse distribution of data, so that that has some implications in terms of how well you can really constrain. We can also look at, say, tidal variability. What's shown right now, this is comparison between NavGem, which is the Navy's sort of high altitude data assimilation system is in black, and then red is a radar observation. And so this is at the Northern Hemisphere site in Germany, and you can see there's lots of this essentially tidal variability on the order of 12 hours, so semi-diurnal tide. And then now we can overlay WACCM in green, and you can see in general both WACCM and the NavGem model show similar variability to the radar in terms of periods when the tide is, say, stronger versus weaker. But there's still, quite a lot of discrepancy, I would say, between the observation and the model. And I should say these observations are strictly independent. So I think one key point here is that the data assimilation models, they generally can agree perhaps with these observations. There are some clear differences, and I think that's important to remember, that since a lot of these observations in the mesosphere are quite sparse, we don't have a full sort of constraint on the model dynamics at those altitudes. We do perhaps better than we might without constraining, but there's still some limitations. And just briefly to mention some of this work on ionosphere assimilation. This is kind of very recent result looking at assimilating ground-based TEC observation. So on the left here, these are synthetic data that we produce from a free-running model, and then we try to assimilate the data and get a better representation. The ionosphere, these are two experiments here on the right. So this left column is if we don't assimilate any ionosphere data, here is a short-term forecast analysis, and then the observation minus forecast. And we can see there's this large, essentially, bias in the ionosphere without assimilating any ionosphere data. But then when we add in the ionosphere assimilation, we can get a state of the ionosphere that's in much better agreement with the observation. And I apologize. I realize now that this is the wrong panel on the left here. This is for a different UT compared to these ones here. So you'll have to just mostly take my word that if we look at the observation minus forecast, we're reducing the error here in the ionosphere assimilation case for the short-term forecast compared to not the case when we don't assimilate any ionosphere data. So we're getting essentially better short-term forecasts when we assimilate ionosphere data. Okay, so now I'll move on to look at a few different essentially science application that we use these models for. So the first is this NO transport during southern stratospheric warmings. And this, one of the motivations for this, looking at this, is that model simulations have sort of consistently had difficulty in simulating the downward transport of NO and NOx during the polar winter. This is comparison of a few different models from our recent paper by Funke. And so the left panels here are the observations, and then these are the three different simulations here on these other three panels. And you can see all of these different model simulations kind of grossly underestimate this downward transport that we see in the observation. So there's something, something missing from the model simulation that is failing to reproduce this downward transport. And one of the questions is that this underestimation may partly be due to poor representation of the MLT dynamics. This, as I discussed previously, but here is then looking at these same 3 simulations compared to the SABRE temperature observations here, and you can see all the simulations basically don't reproduce this sort of location of this elevated stratopause you see in the observation. They tend to be slightly, say, too low or maybe too weak. So, by not fully representing the dynamic variability correct, this may be one of the reasons why the transport is not correctly reproduced in simulation. So if we have a better representation of the MLT dynamics by using data assimilation, we can see if we can get a better representation of the transport. So first, just looking at the representation of the dynamics. So here is specified dynamics. This is during the 2009 Northern Hemisphere winter. So these are basically pressure versus time in the Northern Hemisphere average. This is specified dynamics WACCM-X in the upper left. Then the data assimilation WACCM-X DART in the lower left, and then Aura MLS temperature observation in the upper right. One thing to note, these model results are not at the exact location of the observation, so there's some perhaps discrepancy due to sampling. But you can see in the specified dynamics this elevated stratopause that formed after the stratospheric sudden warming basically drops in altitude quite quickly compared to what we see in the observation and in the data assimilation version. It kind of stays at a higher altitude for a longer period, which indicates we're likely getting better representation of the MLT dynamics. And if we look at the NO transport, this is again the SD WACCM-X on the upper left, and then data assimilation on the lower left here, and then the observation are here on the upper right. And you can see that this sort of tongue that extends downwards is much stronger when we have the data assimilation version of the model compared to without. So it's clear that we're getting a better depiction of the NO transport through using data assimilation. But one thing to note is there's still some underestimation of the downward transport. So this could be related to either the dynamics maybe not fully constrained perfectly yet. There could be still some because the observation are sparse, we may not entirely reproduce the correct dynamical variability, but there could also be questions about source specification that need to be improved. And another aspect we can look at is if we have a better thought of how the model is reproducing the dynamics, we can begin to look at things like the spatial distribution. These are some results from Lynn Harvey, where she has been looking at essentially these previous plots, and what most people have looked at in, say, observation are the zonal mean picture. But recently we have started looking at the spatial distribution of the NO and how it might correspond to differences in the dynamical variability. So on the left are observations, satellite observations, and then the right are the results from WACCM-X. So the colored contour is NO, and then is dashed black and white are geopotential height contours. And you can see in both the observation and the WACCM-X with data assimilation, we see a quite clear sort of a wave number 1 distribution in the nitric oxide that tends to propagate slightly westward, and that's seen in both the model result and as well as the observational result. You can see this sort of clear wave number 1 and this propagation westward. And this seems, these regions of high NO appear to be related to regions with low geopotential height. So there does seem to be this clear sort of spatial distribution that is potentially related to other aspects of dynamics. So one thing we have been looking at are these so-called Lagrangian coherent structures in the lower mesosphere, and how they might be related to the regions of enhanced NO. And so these are basically LCS ridges here indicate essentially these sort of barriers to a horizontal transport. And so here on the left is if we take the dynamical fields, so the winds from WACCM-X and generate where these LCS ridges are, that is this sort of, I guess, yellowish or orange color. And so these are the ridges, and then these are different tracers put in these other lines. And you can see these ones here are sort of confined within this ridge. So they're basically, these ridges form barriers in the transport. And we can see where there's this strong sort of ridge, it tends to correspond to where there's this confinement of the NO here on the right. And these other, I'll show again on the next panel, the next slide. Sorry, so here are 2 snapshots from 2 days in January 2009. These plots are a little complicated, so I'll just step through them. So on the right here is the NO field from WACCM-X with data assimilation. And then the symbols are observation from SOFI and ACE. And so you can see both the observation and the model. There's some disagreement in the absolute values. Again, the model tends to generally underestimate this sort of enhanced region. But in terms of longitudinal structuring, there's general agreement where there's this sort of region of an enhanced NO and a region of smaller NO in the observation and the model. And then on the left here, the gray shading shows geopotential height. And then this, I guess, maybe pink magenta show the LCS ridge. And here there's this sort of strong ridge and this ridge here. And then these circles and the lines are basically tracers that were put in. So the circle is the initial point of the tracer. And you can see these ones here get sort of confined within this kind of region. And similarly here, whereas these ones outside, they're sort of tend to have less confinement and they move. And so it's interesting, these ridges seem to sort of form boundaries around this NO. So it appears like there's maybe this kind of regional confinement that might be related to these sort of barriers in transport. This is something that's, I would say, still quite preliminary, and we're looking at further. These, I would say, are generally quite good cases, and there's some where it's not quite as clear. So we're still looking at this, but it's interesting that you do have a lot of this kind of structuring in NO that does appear to be related to the dynamical variability in some way. So now, another aspect, as I mentioned, is we can use the ensemble to basically provide initial conditions for forecasting. So I'll show some results on that. So we performed a number of essentially hindcast experiments for a 2-year period where we generated analysis fields in WACCM-X start from January 2009 to December 2010. And then initialized hindcasts on the 1st and 15th of each month. So we essentially have, it works out to 47 hindcasts since the last one on the 15th of December, we did not have the full period. And then, so we use this as a way of looking at the forecast capability of the model. One or a few sort of setup things to mention. Here we did not do anything with the ocean sea surface temperature. So they're not being forecasted, they're just specified as truth. So that is, these are essentially hindcasts, and this may impact some of the predictability by just using known sea surface temperature. And for most of this, we'll essentially use the analysis fields as the validation to look at the forecast skill. This is not necessarily ideal, but this is sort of compromised because there's insufficient global observation in the MLT. So we use the analysis since we consider that our sort of best estimate of the true state. But that should be at least taken into consideration. And these experiments give us some insight into potential predictability of the middle atmosphere, and it's a framework that can essentially be used for other application. For example, the sub-seasonal to seasonal predictability. And so I'll present results from first a case study looking at sudden stratospheric warming time period, and then subsequently look at averages for all of the hindcast experiments. So first, looking at the 2009 sudden stratospheric warming, these are plots similar to I showed before, where we have altitude versus time for the northern hemisphere average. And now, so these different panels here are forecasts initialized on a different date prior to the warming. And then the bottom right is the analysis fields for comparison. And these are ensemble averages. And so the white areas then are outside the hindcast time period. And so for these first two initialized, say on January 5 and 10, you can see there's no hint at all of a stratosphere warming. But then on the one indicated on the January 15th, you see it predicts a warming of stratosphere, but also we can see that it predicts this sort of mesospheric response as well. So the cooling of the mesosphere is also shown. So something like 10 days in advance of the warming, we can predict something is going to occur. And then these later hindcasts show a better depiction of the initial warming, and it also captures this kind of, there will be an elevated stratopause following this warming. And looking at the zonal mean, zonal winds shows similar picture. But one thing here you can see in this hindcast initialized on January 15th, that there does predict some sense of a stratosphere warming. The winds don't reverse at 10 hectopascal, so it's not a major warming as seen in the analysis. So it predicts something is going to occur, but not a full major SSW. And just showing that it's sort of a different depiction. Here is just at 60 degrees north and 10 hectopascal. The black dashed line is the analysis, and then these different colored lines show different hindcasts. So you can again see these early few don't predict a stratosphere warming, and then there's this essentially weak warming for the hindcast initialized on the 15th, and then these later ones can predict the stratosphere warming and the timing fairly well. One interesting thing is in this green hindcast initialized on January 25, you actually get quite long sort of sense of the recovery from the warming. Has very good skill, and the ensemble spread indicated by the shading is actually very small. So it's quite a kind of high confidence that you can have predictability. And then looking at the mesosphere, this is temperature at 70 to 90 north at 10 to -4 hectopascal. Again, the dashed is the analysis. And it shows something similar where these early forecasts don't show much in the brown and red that you will have the warming, but then the later ones show that you have this mesosphere cooling and then the recovery as well. And one of the things to briefly mention is that these do tend to give us some skill in predicting the ionospheric variability. Again, I won't go into much detail here, but we get an improvement in the ionospheric total electron content prediction when we can basically forecast the SSW will occur in the lower atmosphere. So now looking at essentially, those are kind of perhaps favorable conditions for forecasting the mesosphere when you have a strong signal like the SSW. So looking at the essentially average over all the hindcast, these show the root mean square error, again, relative to the analysis. So this is at 0.1 hectopascal. These are different regions in the different panels. And then the different colors indicate either the zonal mean in the black and gray. Green is for the essentially large scale waves, and then the purple is the small scale waves, so wave numbers greater than 6. And you can see there's a very clear dependence in how quickly the errors grow. So for the small scale waves, the errors grow quite rapidly, and within a few days essentially saturate, whereas the larger scale and zonal mean, there's essentially the errors grow slower and do not saturate for a longer time period. And so this indicates that our ability to essentially predict the small scale waves is significantly lower than this larger scale variability. So if you want to be able to, if you want to predict, small scale structures, you really have a very short forecast scale compared to larger scales. If we go to higher altitudes now, so this top is a repeat from the previous slide, and then the bottom shows results looking at higher altitude. And you can see that the main point here is that these errors grow much faster for not only the small scales, but even the larger scales. So in the sort of upper mesosphere, lower thermosphere region, your forecast skill and predictability is quite short, on the order of a few days, at least in this setup of the model. So this sort of long predictability we might have seen for the sun stratospheric warming is quite optimistic, and typical predictability of the mesosphere and lower thermosphere might only be on the order of 5 days at most. So it's quite different than lower altitudes. And then last, to look at essentially tides. So we can look at the main tides here, the diurnal migrating tide in the black color, the diurnal semi-diurnal migrating tide in green, and then this DE3 diurnal eastward propagating tide with wave number 3. And so these are tides that can drive a lot of the variability in ionosphere and thermosphere. So that's why they're of a special interest. But these show similar to the previous slides on the larger scale waves where the errors grow quite rapidly and essentially saturate after something like 5 days. So the predictability of the tides that drive a lot of the upper atmosphere variability is quite short, so that that sort of is kind of time range you might be able to predict the tidal variability with the sort of understanding that is kind of current capabilities of WACCM-X, and that this isn't necessarily a limit of predictability. It's essentially current capability. The limit is, I'm not entirely sure what that would be, but it's possible that this maybe could be extended. So just to briefly summarize, data assimilation in WACCM and WACCM-X is advantageous in the sense that it's able to constrain the state of the atmosphere above the domain of existing reanalysis like MIRA or ECMWF. So we can essentially constrain better the mesosphere, thermosphere, and ionosphere. And this is useful for specific scientific studies, but it can also be used to look at predictability of middle and upper atmosphere through initialized forecasts and hindcasts. And some of the ongoing work is related to the NO transport in the mesosphere to basically look at how the connection between the dynamics and chemistry. And then also we've looked at the investigated the forecast skill of the MLT, and it appears to be sort of on the order of a few days in WACCM-X currently. But we plan to do a bit more investigation in the predictability of ionosphere and see what could maybe improve the predictability in the mesosphere as well. And then one thing I think just should be mentioned is that because the observations are still somewhat sparse in the MLT region, this tends to only loosely constrain the MLT. So we don't, we can do a better job, but there's still some work I think to be done in terms of either assimilating new data or better treating the data that we already have, so that we can basically improve the fidelity of the results from the data assimilation as well. So I will stop there and I can take any questions.
Okay, so if you have a question, I can see the chat right now.
Okay, I exit the slide so I can see the chat. Or can you still see the slide?
Yeah. So if you have a question, you could ask it in the chat, or just say you have a question. We'll go around in order, just to keep things orderly. And I can leave that to Nick actually, if you want to just do that. So does anyone have a question? I'll ask a question just verbally. Do you have so those temperature and wind hindcasts of the sudden stratospheric warming and that sort of picture of the mesosphere and stratospheric temperatures, It seems like WACCM is extremely resistant to continuing to sustain the downward propagation of the warming, even when it's starting to happen. Do you have any idea of why it's so resistant to doing that?
No, I have not looked too closely. Though I think in general, I'm not sure if WACCM is necessarily that different compared to other models in terms of its ability to forecast stratosphere warming. I think you might see something the same in another model, but to say that WACCM is different in that sense, I'm not sure is true.
This is Dan. I have a similar follow-on question. I mean, do you think that we can learn what we're missing in terms of our parameterization of physics, or is it a resolution issue that why the model wants to do its own thing rather than reproduce reality?
Do you mean specifically for the warming or for other, just in general?
Just in general, what can we learn about the missing processes or poor parameterization performance in WACCM from comparison with the dart runs?
Well, I think it gives you, a way to have a better sense maybe of what the higher altitudes are doing in as a sort of baseline for comparison, right? So you're, for example, can you see the slide I'm showing now?
Yeah.
Okay. So, right, it's very clear from this that there's a clear bias in the model, right? When you don't include this data. This is kind of a simple, thing to say, but it's clear that you have some bias in terms of, how well you're comparing to how well the temperatures are compared to essentially the observation. And by assimilating the data, you're removing that temperature bias. So while you can compare, say, to Mira up to a certain altitude, data assimilation gives you something to compare to perhaps at higher altitudes. In terms of how that feeds improvement, that's tricky. I think most of this uncertainty in the mesosphere probably comes from gravity waves. I think the study that Anne did show that quite nicely. So, there's potential that you could maybe do something like try to better estimate gravity wave parameterization scheme off of, using the framework of data assimilation. Does that answer your question?
Yeah, thanks.
I just have a quick follow-on to that. Nick, have you looked at the assimilation increments to see if there's spatial or temporal structure to the increments?
That is, in the mesosphere, that's quite difficult because the observations are themselves sort of varying spatially and often temporally, since Sabre, rotates in local time. So I've not looked at that in too much detail, but that is a good idea that you might be able to, with a long enough period, look at sort of average the increments to see if they show some sort of structure.
Yeah. Okay, that's all. Thank you.
Any other questions? All right. Well, if there are no more questions, I wanna thank Nick for agreeing to do this remotely. It's not exactly the most ideal format necessarily to coordinate all this, especially the Q&A. But I appreciate him doing it on a very short notice. And yeah, just a reminder, we do have upcoming remote presentations as well. So check the calendar and watch for announcements. So thank you everyone for coming.
Thank both of you guys too. Bye.
Thank you.